Hello everyone, my name is Farnaz and my presentation is about designing controller for online state tracking in presence of adversarial disturbances. So let me explain this research topic further. What we consider here is the classical state tracking problem in control with the following specifications. Firstly, we consider linear dynamical systems where we know the dynamics A and B, but we assume that this dynamical system is subject to adversarial disturbance. By adversarial disturbance, we mean bounded, unknown, and arbitrary disturbances. And also, we consider a reference signal which is generated by a linear system. We assume that we don't know the dynamics of the reference signal. As a result, we can assume that the dynamics can change at some steps to something else. For this setup that I mentioned, we are interested in designing a controller such that the state of the system tracks the output of the reference signal while minimizing a general convex cost function. So we are interested in optimizing convex cost functions, not necessarily quadratic one. The classical solutions to the tracking problem, they are either optimistic or pessimistic, or they can actually handle quadratic cost only, not general convex cost. So to solve this problem, we propose to parameterize a controller as 5. Let's have a closer look at 5. So we have a state feedback controller here with a feedback gain K, but also we have some feedback from the past disturbances and also feedback from the past values of the reference signal. So this is our proposed controller. And we can show that this controller can actually approximate any state feedback controller from the state of the system and the reference signal. But you may wonder, why are we interested in 5? Why we can use the classical one? Well, the reason is that we can show that the cost function C is convex in the matrices MW and MR. And this is quite important because it helps us to actually use some online, let's say, gradient descent algorithms to optimize the parameter and learn the parameters or adapt to the new disturbances. Here is the thing that we have summarized in our algorithm. So we have an online state tracking algorithm. It's an iterative algorithm, and it starts with selecting a stabilizing controller gain K and selecting matrices MW and MR to arbitrary values. In each iteration, we try to guess a counterfactual cost. The cost if the current controller was applied to the system from the very beginning. Then we try to optimize this counterfactual cost by gradient descent. As I said, we have shown that this is convex with respect to MW and MR, so we can use actually gradient descent to learn the optimal values of MW and MR. So let's see some simulation results. We have a double integrator dynamical system, and we consider the reference signal as shown here. So the reference signal will change at a step 500 to something else. For the case of comparison, we consider a quadratic cost function because we want to compare our results and simulations with the LQR as well. And then we study 3 cases for the disturbance. The first case is to consider constant disturbance. The second case is kind of an amplitude modulation. And the third case is when we have a sinus as kind of for our disturbance. And then in these figures, you can see the tracking error. Our algorithm is shown in red, and the result of the LQR algorithm is shown in green. As you can see in all 3 cases, our algorithm has smaller errors in tracking in comparison with LQR and also H infinity, which are quite similar. So it actually can adapt itself for that specific disturbance, and it can achieve better tracking in comparison with the other controllers. This is my presentation, and thank you for your attention.